Hi, we are the Pegasus Protection Services Senior Design Group here at the University of Central Florida. We are a team of all computer engineers, and our members are Christian Silva, myself Isaiah Williams, Dylan Sauerbrunn, and Andre Fredericks. The objective of our project is to create a security system that can be used to monitor personnel entering and leaving secure locations. This will be done through the use of Bluetooth Low Energy, beacons and tags, as well as facial detection and facial recognition software. And in our demo, we aim to test 4 engineering specifications. The first one being the beacon size. We wanted to have it handheld, so we wanted it no larger than 120 by 70 by 40 millimeters. The second specification is the time it takes to successfully recognize a face. We wanted to have that in less than 5 seconds, and in the demo we achieved about half of a second of time to successfully recognize a face. The third specification is the range that our Bluetooth beacons can detect tags, and as you can see in the picture on the left here, at the bottom we are able to detect a tag that was 10.5 meters away, so we were able to hit that specification. And finally, we wanted to test the accuracy of our indoor positioning software. And as you'll see in the demo again, we were able to achieve about a meter of accuracy between the actual position of the tag and displaying that on the website. And these are our 2 PCB designs. As you can see on the left we have our Gen 1 PCB, which was much larger than our intended size and used an entire ESP32 dev kit module. But we did go back and redo that in our Gen 2 PCB, and we still use the ESP32 as our main module, but now it is powered by a LiPo battery or USB-C cable, and it's now versatile and can be either a beacon or tag depending on what code we upload to it. And the PCB is handheld and comes in at about 50 by 28 by 8 millimeters, so much smaller than our first design. In this demo, we will be using 3 stationary beacons and 2 tags. As you can see, one of our beacons is the first gen PCB, just as a proof that it works, and the other 2 beacons are in second gen PCB. The 2 tags as well are second gen PCBs, and the tags will ideally be held by any personnel that we want to track around that room. And the beacons will search for their Bluetooth signals and send the appropriate data to our web application. And now onto the demo.
So as you can see here, this is the room that we are using to do our indoor tracking. We had to set up each beacon correspondingly to a location. So beacon number 3 will be on the left side of the room. Beacon number 1 will be on the right side of the room. And we gotta switch it on. And beacon number 2 will be on my desk, which is right in the middle of the room on the other end. Switch it on again. And once that is all set up and ready to go, we are ready to move on to our web app. After setting up our 3 beacons, we are now able to get that real-time data onto our web app. So we're going to go ahead here and log in. And here is the home page of the web app once they're signed in. At the top, you'll see our top bar, which includes a profile picture of the user, settings, and alerts, and other notifications that they can receive. On the left, you'll see the sidebar. So home is this page here, which is a dashboard, the live indoor tracking, the live video feed, and then a menu that shows the user in the database, the tags corresponding to the users, reports, and then at the bottom, alerts. Here on the dashboard, on the home page, you will be able to see the latest tracking. So as you can see here, we have 2 tags being detected. We have Christian's tag and tag number 2. From the incoming data, we get that beacon number 1, beacon number 2, and beacon number 3 are constantly sending RSSI data and distance data from their corresponding locations to the web app. As data keeps coming in, the table will constantly update, and you will see that change with the timestamp or the incoming data. And now for our live indoor tracking. As you can see, this is the floor map, the floor plan of the room that we are currently testing in. And as you can see here, 5 icons spawn, 3 of them being beacons and 2 of them being the tags that they are detecting. So each of the beacons was a MAC address. You can go ahead and drag these icons to the corresponding locations. Once they're set up, the people icon here will start moving accordingly to the incoming data coming in, which has to do with the distance and the RSSI it's detecting from each corresponding beacon. After the corresponding beacons are done being placed in the proper location on the web app, as seen here. So in my case, I have one on my desk and two in the corresponding corners. And in this scenario, we have two tags active right now in our system. These two tags will appear on the map as well, with the corresponding location estimated. So really how this works is that each tag emits an RSSI. The beacon is going to read in the tag MAC address as well as the RSSI it's emitting. Using these two data points here, we're able to map them using trilateration. Trilateration uses distance, which we can calculate with the RSSI, and RSSI itself to place them in its proper X, Y, and Z location that corresponds to the map. So as you can see here in my hands, I have a tag. I put that tag in my pocket and I will start walking around the room. There's also another tag on my bed which stays stationary. So the tag nearest my bed, as shown here, circled, will stay stationary throughout the whole duration of this video. Meanwhile, this tag right here will be moving. So as you can see, as I move towards the right side of my room, the tag icon will follow me to that side of the room.
And that concludes the demonstration on real-time tracking on our web application. To add a bit more context, there were several applications or several technologies used to get this functioning. These technologies include, but are not limited to, Arduino, MQTT, React, OpenCV, and Python. MQTT merits a bit more explanation because this software handles our RSSI data. To isolate the microcontrollers to one access point, it must access the broker's IP. Once there, a subscription to the WebSocket is established and data can begin publishing to the host. After the host receives the data, it delivers the received information to the web application. Reaching the end of its path, the process starts again into an endless loop.
MQTT keeps our whole system functional. MQTT is the middleman between our ESP32 and our web app. Without it, we would not be able to get data. What happens is our ESP constantly scans for devices in the area, and with devices that it finds, it sends a pave load of data to our JavaScript, which our JavaScript then breaks down, and we can play around with the data there. So let me show you. So we start up MQTT socket, and automatically we get a connection from our ESP32 client. This client here, let me show you, is constantly scanning, looking for data. It's looking for a system of tags that we coded up. So right now it's just looking for my tag, Christian's tag, BLE tag number 1, and it sends over this pave load here. This pave load here corresponds to E just being everything in this, DD being the detected devices. So it detected this device MAC address here with this RSSI, and then its own MAC address of itself. So coming from this beacon's MAC address. Once received, this data is processed in our receiver.js file, which we break down by detected devices, and we store that string into our tag MAC, and then we do the same thing with our beacon MAC, where we go in there and we find where it came from. And basically what we do is we store it in an object array, which contains our tag MAC and our beacon MAC. We store in the incoming RSSI value with the R, and then the timestamp that it came in, just so we can keep refreshing and keep getting that new incoming data. So as you can see here, our ESP constantly sends over data. Once this data is arrived, we can manipulate it however we want onto our web app. Basically, we break it down with an RSSI and this detected device, and we can then implement our trilateration implementation.
The next piece of the Pegasus Protection Service is facial recognition. In our implementation, we will have preloaded images to identify known faces and unknown. Here's Dylan with a brief demonstration.
Here's an update on the progress we made towards the computer vision component of our system. The first portion depicts the face detection on the test camera. As you can see, the system is fairly capable of detecting my face on the camera. I wanted to test if it could pick out multiple faces from an image on my tablet, and it was able to handle that as well. Next, I present my face at different angles to see if the computer can detect those cases as well. You then see me start to back away from the camera as I try to get a feel for the detection range, and measuring this length showed a distance of around 2 to 3 meters. Next, I wanted to test different accessories on my head and see how well the program could detect my face with those accessories on me. Mask was a fairly surprising result, as even with masks, the face was able to be properly detected by the program. I then begin to test different light conditions. As one might guess, the darker the room is, the harder it is to detect a face. You can already see that with a decrease in brightness, the range also is impacted. The last thing I want to show is how increasing the motion of the person in the camera, it makes it harder for the computer to track a face. When it comes to facial recognition, we can see that the camera runs at a lot slower frames, or at least displays a lot slower. And that's because of the amount of computational power it takes to compare faces it sees on the camera to faces the program has in the database that was pre-established beforehand. Now, when I walk back, you can see that the camera is still pretty accurate in identifying my face. At different angles, you can see the computer having a hard time identifying me, and that's mainly due to the fact that the recognition was trained on frontal images, not profiles. When it comes to accessories, though, the recognition had no problem identifying me, as you can see with me on a beanie, as well as me with a cap, so people shouldn't have to worry about wearing their hats. We even put the facial recognition to the test with me putting a mask on, and to our surprise, from the front it seemed to identify us, and even sometimes from the side it would, but it was never that confident, and it was kind of glitchy from the side angles, so probably avoid masks for the workplace, as sad as that sounds. Next, we wanted to see how our facial recognition performed in lower light conditions. As I gradually dim the light, you can see that it is still able to identify me, but once I get to very dark, the range is completely diminished and it has a harder time even detecting my face to begin with. So yeah, when it comes to motion in face recognition, the blurrier the face is, the harder it got to identify, but in stills, it was able to identify me pretty well.
And that concludes the demonstration on facial recognition. So what's left for the final demo? We need to send alerts to the dashboard when a tag does not line up with the face stored in the backend, make our real-time tracking just that, more real-time, and upload a live video feed to the web app while also connecting facial recognition. Thank you. This concludes our demonstration.